Yeah, I hope the audio is working. Yeah, I think so. It seems to be working. Hello, so today I'm going to be streaming Project Euler, which is a set of problems suggested by a subscriber. They involve maths and programming, which are two subjects that I enjoy. The website is projecteuler.net, so you can check it out and try and solve some for yourself if you want. It's pretty fun. Anyway, we've solved problem 0 to 11. This problem 0 is the problem you solve in order to be able to create an account. So now we're going to solve problem 12, and we're using random programming languages. So before we start, I'm going to spin the wheel. Where's the wheel? Here we go. All right, so the spinner is going to land on a random programming language, and whichever language it lands on, I'm going to use. Let's see what I get. C. Spot on C. All right, so C is the lowest level of all of these languages, and I'm going to go through them again. I did this in the last stream too, but I think it's interesting to know about the different languages. So yeah, C is the lowest level. It's got less boilerplate than Java, but it's definitely the hardest language because it lacks some common libraries such as Big Int. Java is very similar to C#. These two are similar, and they are sort of a middle ground between C and Python, because you don't have to use manual memory management. Python is the tersest of all the languages. It's the easiest to use in my opinion. And JavaScript is similar to Python, just it has a different syntax and some quirks. All right, let's go. I'm going to make a new C project. So it's going to be problem12.c. Problem12.c. All right. Now I just need to swap the windows over to code. All right, here we go. Hello, Patrick. Hello, XNFN. Yes, Patrick says the problems are getting harder. It's true. Okay. Let's see. Highly divisible triangular number. Okay, so I'll make this a bit bigger so we can read it better. And here we go. Sequence of triangular numbers is generated by adding the natural numbers. So natural numbers and positive integers. Well, that's it really. So the positive whole numbers. Anyway, let's continue. The seventh triangular number would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. That's 28. Okay. The first 10 terms would be that. Fair enough. Let's look at the factors of the 7. Okay, so these are the factors of 1, 3, 6, 10, and 15. These. And 28 is the first triangular number to have over 5 factors, because 28 has 6 factors. What is the value of the first triangle to have over 500 divisors? Well, okay, this problem doesn't seem too hard at first, because really we can easily loop through all the triangular numbers. Am I right? Yes, I think we can. So we'll start at 1, add 2 to get 3, add 3 to get 6, add 4 to get 10, and as I hope you can see the pattern, we're just adding we're incrementing the number that we're adding by. Okay, so that'll get us all the triangular numbers. Then we can make a function to figure out what factors the number has, and if it has over 500 divisors or factors, then we're done. We've got the first triangular number. And this shouldn't be too hard in C because you don't really need to manage memory for integers. Let's go. Back to the code. Can I somehow resize this? Oh no. Okay, here we go. So we're going to include the standard library for input and output. Make a main function. Oh, I always make a mistake. Int main. And let's just print hello world to test this out. And this is actually my first C problem. I haven't done any Project Euler problems in C so far, and we've done 12 problems. Okay, so I'm compiling this with GCC. It's problem 12.c, and that's going to generate an exe called ./a.exe, and that says hello world. So we have got it. It's working. Now all we need to do is program the problem. So let's start by looping through and getting all the triangular numbers. I think we can use a for loop for this. No, instead we should use a while loop, actually, because we want to stop when the number has over 500 divisors. So let's see, we'll make a number called n. It's going to be an integer. It's really an unsigned integer, but I prefer just saying int. So while we haven't got a solution, for now I'm just going to say while n is less than, I don't know, 100. Let's add onto n, sorry, not increment. We're going to add another number onto n. Let's call this number x. X is going to start at, oh wait, n should start at 1, because the first triangular number is 1, right? And x is going to start at, how do we get the triangular numbers? 2, there we go. And we're going to add x onto n, and then we're going to add 1 to x, so x plus plus. And let's run this. We should get a bunch of triangular numbers under 100. It's still telling me hello world for some reason. Oh, I'm sorry, I forgot to print n after every iteration of this while loop, and I didn't mention that C is actually my favorite language. I find the danger for all the different stuff you can abuse fun. Okay, we forgot to have the /n, and it's also interesting to see how the different low-level stuff works in a computer. Okay, so we got 3, 6, 10, 15. These are correct. These are triangular numbers. However, we started at 3, so I need to move this print statement up a bit. Just one line before we add x onto n, and there we go, we've got our triangular numbers. Great, we can remove this hello world. And let's see, what are we going to do now? Yes, we want to find a function, or make a function, to find the factors of a number. Okay, so I'm going to call it num factors, and yes, I know that actually I'm not sure. I'm not sure this is the correct case for C, but I like using camel case. It doesn't really matter as long as it's consistent. So num factors of n, and we're gonna We're going to loop through a bunch of possible factors for n. We're going to start at 2 because every number has... Or not? Should we start at 1? Does 1 count as a factor here? Oh, it does. Okay, so we're going to start at 1. I is going to start at 1. FN says divide the number by a bunch of numbers and check if it's a float or an int. Yes, that could work. Oh, that is pretty much what we're going to do. We're going to do something a bit more efficient though, which I'll show you later. Okay, so while I is less than, and a nice optimization here is we can, less than or equal to, we can take the square root of the, one second. So we're going to take the ceiling to cast it to an integer of the square root, oh no namespace, you can see, the ceiling of the square root of n. Okay, and that's the upper bound for a small divisor. And we can just multiply our result by 2. And hopefully that should work. I'm not going to call this variable n, I'm going to call it k. And so now we're going to see if k is a divisor of n. Is k a factor of n? And the way we can do that is by dividing n by k and checking if the remainder of the division is 0. So if it's perfectly divisible. And the way we can do that is using the modulus operator. Hopefully that makes sense. And if that is true, then we're going to increment the result. We can make a variable called result. It starts at 0. So I'm going to increment the result by 2 because we've just found a pair of factors. For example, I'll make a comment here. For example, for 12, if we, no, that's a bad example. 16, maybe 20. Okay, no, that doesn't have a nice square root either. 25. Okay, 25. So the square root of 25 is 5, which means the upper bound of our checking is 5. And that's good. So we're going to check 1, we're going to check 2, we're going to check 3, 4, and 5. We'll find that 1 is good. So 1, we'll take that. 2 is not good. And the only numbers that actually work are 1 and 5. So 1 results in another pair of 25, and 5 results in 5. So our result is 4 factors, and I'm pretty sure that's correct. Is it? It is. Okay, so let's return our result, and we're going to test this function. It's very important to test your functions. So I'm going to print the number of factors that the function returns for 1, 3, 6. Well, really all the triangular numbers that we have here on the left. So 1, 3, 10, 15, 21. Really, that's enough, but I guess it's been complete. And oh no, we got a warning. Type of n defaults to int. Oops, I forgot to say int n. Too much coding in Python. Patrick Wellborn says, but 25 has 3 factors. And he's right, because 5 is not a factor that's doubled. So we don't want to double count 5. And so if we get to the square root, we're just going to add result, increment result once, not twice. So what we can say is, if I'm going to make a variable here so we don't double calculate the square root. I'm going to call it k square root, and it is going to be this. Did I copy that properly? No, I don't think I did. Okay, n square root. So if k, which is our current factor, is the same as n square root, then we're going to increase the result by 1. Oh no, that's not. We only want to increase the result if it's a factor. Oh, okay, I'll add this in here. So if there we go. Otherwise, we'll increase result by 2. So if k is the square root of n, we'll increase the result by 2, because we don't want to double count the square root, it's just 5 and 5. Otherwise, we'll just increase the result by 2. And now I'm not going to use the plus plus operator here, just so we can be consistent. I think it's a bit cleaner. Let's see. 1, 3, 6, 10, 15, 21. What are we doing here? Oh, I forgot to print a new line, so I'm going to add that now. We have 1, which is correct for 1, 2, 4, correct for 6, 4, 4, 4, that's 3 fours, and 6. So we're good. That's great. The numFactors function seems to work. Let's get rid of all this testing. We can recomment it later. And let's see which. I think we could use a do while. Does C have a do while loop? It does have a do while loop. Okay, so what we want to do is set the numFactors variable. I'm gonna call it n. No, I'm gonna call it numFactors, and it's gonna be defaulted to 0. So we're going to find out how many factors n has, so 4. Sorry, numFactors, we're going to set that. Oh no, I'm duplicating this. I can't make a variable with the same name as a function. That would be bad. So instead, I'm going to call the function get numFactors. I think that's a better name. Get numFactors. For a specific integer n. Get numFactors of n. Okay, and that should work. Now, we're gonna do that while the number of factors is less than 5. Okay, so we should get a result of n being 28. Oh, I forgot to increment n. I forgot to get the next number. Really. Okay, so let's see if that works. We should get 28. We got nothing because I didn't print anything. So I'll uncomment the printing. And we got 10. Well, 10 is definitely wrong. Let's see why. I could have made 2 1-by-off errors, but that's unlikely. Let's see. I think there's a core logic error in here. So, let's see. Well, we want to stop when a number has over 5 divisors, not 4 divisors. So if we want it to be over 5 divisors, we should make while n is less than 6. Now that gives us a result of 36. Oh yeah, so before we were going for 4 divisors, and 10 is the lowest number with 4 divisors. Alright, that's fixed now, and I'm pretty sure we've got the core logic down. Not sure why this do loops formatted like that. Okay, now I just want to change the 6 to big number, which is 500. So we want to get 500 factors. Oh no, I accidentally removed the print statement, but I'm pretty sure we're almost done here. Printf. I gotta use the formatting, otherwise I'll put the break. Okay, and this is our result. So this is the first triangular number with over 500 divisors, hopefully. Oops, I made a mistake. It should be 500 plus 1. Plus 1. And let's test this again with 5 devices. And we get 36. Oh no, 36 is incorrect. We're supposed to get 28. That's my bad. Well, what's our mistake? Let's see. Is 36 even a triangular number? 28 is... What's 28 plus 8? So 36 is a triangular number. How many factors does 36 have, though? Let's think about that. Oh, you know what? Let's just use a debug statement. So n and factors. So that's pretty good debugging, I think. N factors. Oops, I forgot to add a new line. Alright, here we go. So, it says here 28 has 6 factors, but we never actually run get num factors for 36 because we're incrementing n after we've gotten the number of factors. So we don't want to do that. Instead, we want to increment, or not increment, sorry, increment is the wrong word. I want to add on to n before we get the number of factors, and now we should get the correct answer, which is 28. And we did. Great. Okay. Let's change this number from 5 to 500. And it took a couple of seconds, well, less than a couple of seconds, but we got a result, and this is a number with probably a lot of factors. Let's type it into the answer box, and is it right or is it not? Drum roll, yeah. Drum roll. And it is correct. Cool. Still has a difficulty rating of 5%, but that's okay. Maybe we'll get to 6% for the next problem, which is called large sum. Oh, wow, look at that number. Wow, that's a big number. That's a really big number. Oh, okay, I'm scrolling and I still see the big number. You know what, we need more screen space for this. So I'm gonna show you the problem. Zoom in a bit. Okay. Work out the first 10 digits of the sum of the following 150-digit numbers. Okay, so really, I want to sum this. Get the first 10 digits. Patrick Wellburn says, well done, thank you. Okay, so at first glance, I think, so this problem is really hard for a couple of reasons. Well, really one big reason. And that big reason is computers deal with usually 64-bit integers. And that means the maximum value for an integer is going to be 2 to the power of 64. That's an unsigned integer. So if these numbers are definitely bigger than 2 to the power of 64. So we could use a bigint library, and that might work. Yeah, that would definitely work. But here's the second problem. I don't know if it's the second problem, but here's the challenge. If we get C, it's going to be really hard because C does not have a bigint library. So it's going to be really hard to sum this. And it may seem like you only really have to sum the first 11 digits because it says work out the first 10 digits, or maybe the first 12 or 13 digits. But that's wrong, because think about this, right? Think about this for a second. What if we summed, and this is why we have to think about every single digit of these numbers. Because what if we summed all these numbers and the result was on a boundary? For example, all these digits were 999. I mean 99999. And that's why we have to consider every single digit, even these ones here. Alright, so let's spin the wheel, see if we get C or not. If we get C, this problem is going to take 5 times longer than with any other of the languages. Except maybe Java. Java took a long time last time, but now I know how to use Java big integers. Okay, let's swap over to the wheel. Wheel, please give us a good language. Well, all of them are good. Let's see what the wheel gives us. We got Java. Okay, it was one off from C, although the distance is pretty big. Alright, Java's great. Let's make a new Java file. In VS Code. And it's going to be problem13.java. And I'm going to have to type out all of that boring boilerplate, which we all love. Well, some of us, not me. Actually, I don't know who loves it. Anyway, it's static void main. No, public static void main int. No, it's a string array. String array args. Let's test this by printing something funny. I don't know about funny. I can't think of anything funny right now. We can print. I'm just resizing the display. We can print hello. No. Okay, hello. Oh, I have to run it. So Java problem13.java, and we got hello. We actually got the hello. That deserves a wow. Okay, let's go. What are we doing here? We want to get all of these numbers into Java. It's going to be an array of integers. So I'm going to make a new array called nums. And it's... Why is my tab broken so much? This is messed up. Oh, there we go. I fixed it by formatting. Okay, so it's going to be an array. Oh, no, it's going to be an array of big integers. For now, let's just make them integers. And then we'll change it. Int nums. It's going to be an array. I think that's how you declare arrays. Let's say 123, 42. And we have to use the array initialization syntax, so it's going to be something like that. No. Like that. Not like that. Syntax toka. Syntax error on token int. Oh, it's an int array. That's... Maybe now it'll work? Yes, it worked. Okay, and now we want to sum nums. Well, let's use Java's big int library. Big integer, it's going to be a big integer array. And I'm not sure why it doesn't like that. Maybe if I say new big integer. Perhaps that's right. No, that's not right either. Oh, I have to change this. Oh, I have to use square brackets. It's telling me. Good, there we go, that's great. Now, for our numbers, I'm gonna use big integer dot value of. And this is a great function, a static function I discovered yesterday in my stream. It took me a very long time to find it, but I got there eventually. Okay, so this is working. Now we want to sum nums. no, but before we mess up our code space with all of these huge numbers, let's write the logic, which is not that difficult. Okay, so we're gonna use a for loop. Do we want to use a for loop? Yeah, I think we want to use a for loop. Okay, so we're gonna loop over each big integer. So for big integer num through in. Do we have an off keyword in Java? I don't think so. Okay, we're gonna use a normal for loop then. So for I. For index starts at 0, it's less than nums.len. Print I every loop. Okay, so now we can find the number. So the number, which is going to be a big integer, it's going to be the ith, if that's a word. I think ith, you say ith, yeah. It's going to be the ith big integer. It feels weird to say ith. Anyway, we're going to add the number to our sum, and the sum is going to be another big integer. So big integer sum starts at 0. Oh wait, sorry, we're gonna make it start at big integer dot 0. 0 is some static constant, which is just a big integer with a value 0. And what are we doing now? We want to add onto the sum the number. However, this does not actually modify sum, it's in place, so we want to change sum ourselves to the result of sum.add. Whatever add returns, we'll make sum. We'll set sum to that. And we should get 123 plus 321, which is 444 once we print this. So I'm going to go system.out.println sum. And I believe that you can print big integers. I'm sure they implemented some sort of print method. 444, that's what we got. Great. So now let's input these huge numbers into the numbers array. I'm going to copy them. 1 second. Not sure you can see me doing this, so I'm gonna try and change it. Okay, it's okay. I copied them now, and they should be on my clipboard. And now I'm going to change. I'm just gonna paste it. I'm gonna dump it all in there. Okay, that worked. Now I'm going to just fix the indentation for my document. Oh no, that's not gonna help me. Okay, I fixed the indentation. Oh no, I think I need to make it a bit smaller so everything fits in the screen. Okay, so that's one. Now I want to indent everything again. Again, there we go. Now it's all neatly aligned. So we'll go. And yes, this is a lot of function calls, but Java's gonna hopefully optimize this. Maybe, actually, I can't think of any way to optimize this. Let's see. It's going to be big integer dot value of this number, and to the end of each number, I'm going to end a closing bracket and a comma. Well, we have a lot of numbers. I believe 100. Yeah, 100. Okay, so we had a closing bracket and a comma. Now it's giving me an error. Oh, my bad. I have to make this a string. That's the whole reason why we're using big integer. So it's actually going to be new big integer. I think I have to change everything. Should I make a macro? I guess I could use mod s within them, but I'm not bothered. Let's go and do this the lazy way. New big integer. And it's going to be constructed with that value, and now I'm going to change this to string so that we can actually represent it. Okay, let's change them all into string, and I'll turn off word wrap. Oh, that's much better. Okay, and now I finally need to add a closing quote. And that should be all. Are we done? Is that it? We've got a lot of duplication, but I think we're done, and it looks great. To me, anyway. Okay, let's see what our sum is. It's going to be pretty huge. Yep, this is the sum. We want to get the first 10 digits of the sum. I'm just going to count with my cursor. Wait, I think I can make this a bit bigger. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10. 3, 6, 10. Okay. We can zoom back out. Okay. We'll plug that into the answer and hit check. If this is correct, I'm gonna play a sound effect. Yes, it's correct. There's the sound effect. Great. Okay, now we're doing problem 14. For problem 14. Oh, and we're still on a difficulty rating of 5% after 14 problems. Well, 13. I guess it's 14 if you include problem 0. Also, guys, please like. It helps the algorithm. Okay, here we go. Longest Collatz sequence. Let's make this bigger. Oh no. Come on. Come on. No, it's not. Ah, there we go. Great. And I just want to... Okay. So, this is the Collatz sequence here. If n is even, then we are going to divide n by 2. If n is odd, we multiply n by 3, and we add 1. It's pretty simple, and each Collatz sequence is thought to end at 1. But it hasn't been proved yet. It seems like a simple problem, although it's very hard to prove. Okay, let's see. If we start with 13, this is odd, so multiply it by 3 and add 1. Even, divide by 2, divide by 2, divide by 2. Multiply by 3 and add 1. Alright, that makes sense. Which starting number under 1 million produces the longest chain? And once the chain starts, the terms may go above 1 million. Okay, well, let's think about how we're going to approach this problem. So, I think there is no way to do this except brute force. Maybe there is an extremely clever way, but it's definitely not worth trying to figure out now. Because just doing 1 million of these Collatz sequences should be pretty fast. So we'll loop from 1 to 1 million, and we'll check the length of the chain. We can do that by making some function to figure out the length of the chain. And then we'll find out which of these numbers gives us the longest chain. And I'm quite curious how long the chain is going to be. I estimate 1,000 terms. But that's a very rough guess. I just pulled a number from the back of my brain. It could be more. It could be maybe even 1 million. We'll see. let's spin the wheel and get a language. Last time we got Java. What are we gonna get now? JavaScript. Oh, C again. We landed pretty close to the middle. So it really wants us to use C. So we're gonna use C. Let's make a C file. It's problem 14. Problem 14. We're going pretty fast, I think. Problem 14. Well, not that fast actually. I just looked at the time. It's just time goes fast. Okay. I'll move back to the coding window. And yes, it worked. Okay, great. So what we want here, we'll generate the C, include standard input and output, so we can use printf. Then we'll generate the main function. It's gonna take in nothing. We don't need the arguments. Also, let's return 0. I forgot that we're not actually returning 0. It does not matter whether we do it or not, but I think it's good practice. Ixon FN asks, what code language did we land on? It's C again, yes. The previous question was Java, and now we got C. Okay, so we're gonna loop in for n, and we're gonna go from 1. To test this, to see which number produces a largest collapse sequence, let's test it for 100, because it's always good to test for smaller numbers. It really helps. Okay, so what are we doing? We want to make a function to find out the length of a collapse sequence. And let's call it int collapse. I'm not sure I'm saying the name correctly. If I'm not, someone in the chat can correct me. It's so collapse sequence length, and I'm gonna make it get. That's a pretty long name actually for a function. Okay. We're gonna do it for an integer called n. And so let's remember, if n is even, which means the remainder of division by 2 is 0. If n is even, then we're going to divide n by 2. If n is odd, we'll multiply n by 3, 1, and we'll keep going until n is 1 or 2. 1. Until n equals 1. Great. Okay, so we're going to start. We're going to loop while n is not equal to 1. We're going to keep going with this. So, 1 second, I need to update my text. There we go. Here we go. So while n is not equal to 1, we're going to either divide by 2 or multiply by n by 3 and add 1. So let's first divide n by 2. Let's check for if n is even. So if n can be divided by 2 with a remainder of 0, n is even, and we're going to divide n by 2. So n is going to be divided by 2. n divided by is assigned to 2. And if otherwise, n is definitely odd, and the remainder of division was 1. So we're going to set n to 3n plus 1. So n times is assigned to n times 3 plus 1. And I think actually it's clearer if we say n is assigned to n over 2. Alright, that should work. And with every new iteration of the while loop, we're going to increment the result because we've gotten a new term for the collapse sequence. And in the end, we're going to return the result. So let's see, let's do some testing to see what is the length of the collapse sequence for each number under 100. So get collapse sequence length of, this should go from 0 to 99. I'll compile it to gcc 14.c, and then after that we'll run exe, which is a.exe. And it seems to be doing something. I think, oh no, I think it got stuck in a while true loop. Yeah, because you're never gonna make 0. I mean, you're never gonna make n is 1 if you start at 0. So we're gonna start n at 1. And that's, for n is 1, we're just gonna skip this whole while loop. But for n is 0, it's gonna keep going into this while loop, so that would be bad. Alright, let's see if it works now. And it did work. Let's print a new line so we can see the numbers properly. We get 0. Okay, so 1 has a length of 0. 1, 7, 2, 5. Okay, that's interesting. Let's see if it's correct. Do we have any reference here for Project Euler? We do. It's here. So let's test it with 13. And 13 should give us how many? 1, 2, 3, 4, 5, 6, 10 terms. And instead we got 9. Well, 9 is definitely wrong because 9 is not 10. I think we have to start our result at 1. Do we have to start it at 1? Yes, because we also have to include n in the sequence. N is also a term. Okay, now it should give us 10. And actually, 1 gives us a length of 0. Right? No, 1 gives us a length of 1, because it's just 1. Now, let's test the for loop again. Oh, well, we're getting some pretty long sequences here. 112. Okay. Let's see. 1, 2, 8. Yeah, that seems correct. So let's loop now from 1 to 1,000,000. And we'll see which number gives us the best length. But in order to find out which number gives us the best length, we're going to keep track of the best sequence length so far. So if I'm going to make a variable here called length, which is the length of the of the sequence produced by n. So if the length is greater than the best length, then we're going to set the new best length to length. And also we want to say the best n. We're also going to update the best n. So the new best n is going to be that current n. So if we look at 1, 1 is going to be greater than 0. And then we're going to update the length. Oh no, this is wrong. Best n. We want to update best n instead of n. I mean, instead of best, sorry. Let's see. Oops. Okay, that should work. Now, I'm going to print what the best n we get, and the best length we get for n. So, and the best length is going to be another decimal. So, best and best 10. Oh no, other way around, right? Best 10. I should have named best something better. It's definitely not the best name. Do you see what I did there? Ah. Okay, so from 1 to 100, the best number is 97, which gives us a length of 119. 119 for the length of n. Okay, great. So, now let's change the loop to, instead of using 100, I want to use 1 million. 1 million is pretty big. We want to use less than equal to, because, no, we don't. We want to use less than, actually, because it's under 1 million. Great. Let's test out if that works. How close is my prediction? And it is running. I feel like it should have been done by now. Why is this taking so long? Are we getting stuck in a... This is C, this is not Python. Are the programming gods getting confused, or did I make a mistake? I think it's probably the latter. Let's debug this code. So, I don't think it's an issue with this. Although this is giving the symptoms of a while true loop. So actually, no, I changed my mind. It is an issue with this. What could be wrong with it? Did I type 1 million correctly? Yeah, I typed 1 million correctly. Okay, let's use some print statements to see why this is going wrong. So I'm gonna print the new best end that we're finding every time we find a better version of n. Okay, so all the numbers up until 10,000, well, up until this number, were almost instant, and that gave us a length of 324. But the number after that was not. Well, it got stuck then. So that seems like a while true loop. Let's see. What's the mistake? You know what? Let's print n instead of the best n. That's better. Okay. We'll just print n and its length. Okay, we are getting new n's. Oh, and yet get stuck at this number plus 1. So let's just debug that case. Wait a minute. You know, if the code is working correctly, this number, we might have found an answer for the Colette problem. But that's very unlikely. So let's actually debug it. It's this number plus 1. Okay, so we're gonna test it. Maharali says, just simply create your own function which adds numbers as strings. Not sure what that means. Okay. Could we have gotten a memory overflow? I don't think so. Okay, so this is the number that's not working well. Let's test it. I'm just gonna remove this for loop and all this stuff too. We'll use that later. So I'm gonna get the collect sequence for that number, and it should get stuck. It does get stuck. Not sure why. Let's get some breakpoints. Oh no, let's not use breakpoints. We don't need breakpoints for this problem. Let's do some debugging in here. We'll print what n is all the time. So n, it should be giving me a lot of different n's. It is. Oh no! It's giving me negative n's. You know what that means? That sounds like we've got an overflow error. So let's change the int. What's the upper bound for an integer? See, they're 32 bits, right? Are they? Chat, can someone tell me what the length of an integer is in C? While I update this. Let's make them unsigned integers. That should give us double the memory. But you know what? If we wanted even more memory, we could use an unsigned long integer. Does that work? Can we have an unsigned long integer? Is that a thing? It is a thing, but it takes a long time to type out, so I'm just gonna use long instead. Long int. And we don't need long int for the result. We want long int for n. So I'm gonna make n a long int, and this in different languages, this is called long. Oh wait, is it working now with long? Oh, it is. Okay. Can I make a U on there? No. Oh, it just wasn't working for Euler, but it works with long. Okay. And it's gonna return a normal integer. So now in my for loop, I'm going to make n a long, and I'm also going to make the best n a long and best. No, the length of a collect sequence is not going to overflow int, so it's okay. Let's see. Length int, that seems okay. Let's see if it works now. Oh no. I didn't mean to uncomment all that. Let's just test it with the number that was not working before. Oh no, we're still getting negative numbers. Ah, that's not good. Whoa, it looks like this number is being cast to an integer. Well, I want to cast it as a long. This function accepts longs. Still not working. Okay, let's find what is the range of an int in C? It is it can go up to 1 million. Well, 2 million actually. So oh, I'm confused with this table. Why is it so? Oh, it was just Sam didn't have too much. Okay, well, I guess int depends on your operating system, what size integer is. Well, you know what? Let's see how n first becomes negative, and then we'll see if it is an overflow error or not. So if I scroll up all the way to the top, oh no, it overflowed the console buffer. Oh, still okay. I'm gonna start it and I'm gonna stop it very quickly, so we don't have too many numbers. Oh my god, that didn't work. Okay, I'm gonna start it and I'm gonna stop it even quicker than I stopped it last time. Still didn't work. Let's yeah, maybe that'll give us some more memory. No. Okay, let's just have a break here. So if n is less than or equal to 0, because n should never be 0, then we're going to print n. We're going to print n as a decimal. And let's run this. Okay, so that seemed to work. But I also want to return. I want to stop as soon as we get a negative number. Okay, well, here's our answer. The n in the sequence is overflowing int. It also is overflowing long. So I think what we want is an unsigned long integer. Ooh. Yeah, that could work. Let's see, what are the different data types for an integer in C? Unsigned int. Oh wait, unsigned long will definitely be big enough in this case. Because that's a huge number. I really doubt that n is going to get bigger than this. So we're going to use an unsigned. I wish there was an easier way to represent this type in C, but I guess not. Unsigned. Well, we don't really need to cast, do we? It's okay. Cast anyway. And it worked. N never got under 0. Oh, or did it? Oh, we got a warning. Return with no value. Oh, okay, well that's just debugging. We don't need that anymore because we solved the problem. Or the one problem that we had. Don't forget to like, guys. Okay, let's see. That should work now. Let's run it with the whole thing. And n is going to be implicitly cast. I'm pretty sure when it's passed into this function. So I'm not going to cast it. I think it's a question of style, really. And let's remove the print statements because they take longer to run than the actual function. Oh, I thought I removed the print statements. Are there some in here? Yeah. Okay. There we go. Okay, so this number here, 837799 gave us a collapse sequence with a length of 525. So my guess of 1,000 was actually pretty close. It was half of my guess, approximately. Let's check if this is correct. Drum roll. Oh no, it's okay. It is correct. We got it. That deserves 2 sound effects. Ah, yes, 2 sound effects. Okay. Patrick says nice debugging. Thank you, Patrick. Okay. Let's see now. Next problem. Problem 15, and I'm gonna update my text. Problem 15. So we'll go back to the archives. Lattice parts, number 15. And I'll make this bigger. It's always nice to have a big problem. Well, I'm not big problem as in a big problem, but you know what I mean. Okay. So starting in the top left corner of a 2x2 grid, like one of these grids, only being able to move right and down, so that's either this way. Can you see my cursor? Yeah, you can. Okay, so either this way or this way. There are 6 routes from the top left corner to the bottom left corner, and these are the 6 routes. How many such routes are there on a through a 20 by 20 grid? Wow. It's gonna be a lot. Well, let's think about this. I think this is the hardest problem we've encountered so far. So for each route, we have two choices. Let's close these tabs. We don't need them. So for each step, we have two choices, which is either to go right or down. We're gonna make for a 2x2 grid 4 steps, and for a 20x20 grid 40 steps. And right, the only other requirement is that we need the same number of right steps as down steps. So for a 2x2 grid, we want 2 right steps and 2 down steps. And for a 20x20 grid, you guessed it, we want 20 right steps and we want 20 down steps. Okay, so how can we brute force this? How can we... you know what? Let's not even try and do that. I think that's a bad idea. Let's see. Oh, I have an idea. Okay, I'm gonna make a new text file for this, just so we can make some notes. Go back to the code. Okay, so for this problem, we have... Let's think about the 2x2 problem. So we can either go up or down. So the different combinations are up, down. There's also up, down. Oh no, up, down. That's number 2. There's up, down, up. There's 6 of these in total. And the order, does the order matter? Yes, the order matters very much. Down. No, the order does the... Oh yeah, the order matters. Okay. Down. Wait a minute. I didn't mean to say up, I meant to say right. Okay, let's just replace everything, all the ups with rights, and it'll be less confusing. Okay. So what is it? Down, right, down. Oh no, I didn't mean to do that. Then down, right. There's actually more. I wouldn't... This is a lot of combinations. Imagine brute forcing this. Down, right. Okay. Here's all our combinations. Now this is a lot. This is really what's displayed on the right side of the screen, just in a different format. And let's see, are there any patterns here? I'm not sure, but I think, yeah. I got it. The way we can figure out how many of these different routes there are, it's the same as the number of ways that you can arrange 2 rights and 2 downs in a 4, if you have 4 spaces. So this becomes a combinatorics problem. I think that's what it's called. It's another thing I was reading in my maths textbook. It's a very nice textbook. So we can use... Let's think about this carefully. It's quite complicated. Okay, let's think about this in terms of spots. So we have all different... We have spot 1, we have spot 2, we have spot 3, we have spot 4. I don't know why I made a comment there. This is a text file, but it's okay. So for the first spot at the start, we're going to have 4 choices. For the second spot at the start, we're going to have 3 choices. Then 2, then 1. Oh. Okay, so in this case, in the bottom, 4 choices, which is D. We're left with D, R, R as choices. Third, spot 2, we have 3 choices, which is D. Spot 3, we have 2 choices, which are R and R, which is R, because that's still the choice. And finally, which is R again. Now, if we had 4 different directions, up, down, left, right, the answer would be 4 choices times 3 choices times 2 choices times 1 choice. I think. No, I'm wrong. Am I wrong? Yeah, I'm pretty sure I'm wrong. Okay, I have to think about this problem in a different way. But I'm pretty sure we can still use combinatorics. And I think we're along the right track. So, for the first spot, we have 4 choices. But this... No, do we? Really, for the first spot, we have 2 choices. And 2 for all the spots. Except the last spot. What could be different? You know what? I'm gonna take a break, and I'll think about it and take a break. It's been an hour already, and then I'll come back. Okay, see you in a few minutes. I'll be right back. Hello? Okay, I'm back. So, if we think of this as... One second. Okay, so if we think of this as 4 separate directions, each of which we can use once. So I'm going to say D1 and D2, R1 and R2. Then we would have 4 choices for the first slot, 3 choices for the second slot, 2 choices for the third slot, and 1 choice for the fourth slot. So that gives us 4 times 3 times 2 times 1 options, which is 4 factorial. 4 factorial, and that's the same as 24. Right, okay. So now, but that's not the case. We're double counting here. So we want to divide by how much we're double counting. And we're double counting by 2 factorial ways, because there are 2 different things here. So we'll divide 24 by 2 factorial to get 12. But is that right? That's not right, because we have 6 different combinations here. If we include this. So I must have made a mistake somehow. Why is my mistake? Number of different ways. Oh, you know what? This problem is it's just the number of different ways we can arrange 20 items, well, in this case, 2 items, in 4 sort of buckets. And actually, there's a very easy way to find that out. It's the same as 4C2, 4 combination 2. And we can figure that out using a calculator. So I'm going to go to my Desmos calculator and we'll type in 4. I'm sure we have some sort of C. Where's the C? NCR. Okay, so it's going to be called as a function. NCR 4 and 2. Where's the comma? There we go. 4 and 2. There we go, 6. And that is correct. I hope you can see it. I think you can. Okay, next, we'll calculate what if we have 20 different moves and that's a lot. Okay, so what if we had 20 different, let's say, right moves, and we wanted to arrange that amongst 40 total moves? And that means we would get this big number of moves, which is in standard form. We don't want it in standard form, we want it exactly. Is there a way I could increase the number of the size of the number before it goes to standard form? No. I guess we can put this into Google. NCR of 40 and 20. Combination calculator. Okay. So we have 40 items. We want to select 20. I don't want a list of solutions. Oh, God. Maybe if I say 40C20. Yes, I want the binomial coefficient. Okay. Does this match? Yes, these two numbers match. So it's this number here. Good. Let's go back to the code. So 40, 20 is that. Copy that. And let's paste it. Oh, I didn't copy it properly, did I? We'll paste it in. Let's see if it's correct. That took a while, so it deserves a drum roll. And it is correct. Oh, we're still at a difficulty rating of 5%. Maybe at some point we'll get 6%. Okay. Let's go. Return to problems page. Next problem. Problem 16. Oh. So we solved problem 15 without programming. Cool. Oh, well, okay. So, you know, the first thing that I saw when I looked at this problem was 2 to the 1000, because that's not something you see every day. Well, for most people. Okay, so let's read the whole question. 2 to the 15 is this number. The sum of the digits of this number is 3 plus 2 plus 7 plus 6 plus 8, which is 26. That's 2 to the 15. Now, what's the sum of the digits of the number 2 to the 1000? Okay. Well, let's see. We can definitely do this using bigint. We just multiply 2 by itself 1000 times. Well, 999 times actually. But remember, C doesn't have bigint, so if we get this problem in C, there is an implementation which we just double each digit starting from the right, and then we carry the remainder. I think that will work. Okay, let's see what language we get. Another drum roll. Drum roll. There's 2. There's a bad drum roll. Anyway, we got Python. Okay, so Python is actually the best language for this. I will explain why. The reason Python is the best language for this is because oh no, I accidentally pressed the thing again. Well, this doesn't count. I didn't mean to press the button. So we're using Python. Okay, so the reason why Python is the best language is because in Python, integers can be of any size. It's adaptive. So I'll make a new Python file. It's problem 16, right? Problem 16.py. And okay, so for example, in Python, you could have an integer literal that big and it doesn't complain. It just automatically resizes it for you. Look, this it's like magic. Pi problem 16.py. Look, you see it worked. It printed that huge integer, which is definitely not a 32-bit integer. I don't think, or a 60, maybe a 64. I don't know. Anyway, but we want to represent a 1000-bit integer. 2 to the power of 1000. And you know what? I'm gonna do this in a fancy way. I think it's more efficient if we use a bit shift. So I'm gonna bit shift the binary number 1, which is the same as the decimal number 1, but I think it's easier we think in binary. So I'm gonna shift it. That means 1. If I shifted it right by 1 position, that's 2 to the 1. If I shifted it right by 1,000 positions, that's 2 to the 1,000. Wait, let's see if it works for, let's say, 2 to the 5. We should get 35. I mean 32. 30, and we did get 32. So it should also work for 2 to the 1,000. And it did. It was instant, because computers are pretty good at shifting bits, even if it's not... Well, I'm not sure how that worked, but it worked anyway. Okay, so I'm gonna get this number. I'll convert it to a string, and I'm going to sum the digits of the string. And I think this problem can be solved in 1 line in Python. That would be cool, right? So I'm gonna sum each digit individually. Okay, so each digit individually. For C for character. Now let's see, D for digit. For D in this big string, we want to say convert it to an integer. And let's test this with 2 to the 10, which I think is 1024. That's 2 to the 10. It's nice to have Google calculator. Yes, it is 1024. Okay. So, this array compression thing, magical for loop. Why isn't it working? It's telling me I didn't close the bracket. Open bracket, I mean. But I did close it. I closed it here. Let's just see. Python array compression. So this should convert every digit in the string to an integer, and then I can use the sum function on that. But my internet isn't working for some reason. Ah, there we go. Is it not called array compression? For loop compression. Comprehension. Is it comprehension? List, it's called list comprehension. I was so wrong. Okay, this int d goes at the start of the loop. And there we go, that doesn't give us any syntax errors anymore. So it's going to take the integer version of d for every digit in that string. And then we're going to sum it. Let's figure this out by ourselves. So it's 1 plus 0 plus 2 plus 4, which is 7. Let's see if it gives us 7. Invalid syntax. Oh, I forgot to open bracket for the function. Okay, and we did get 7, and that was actually instant. Yeah, let's see if it's gonna be instant for 1,000. It was instant. Great. Okay. I think we're done with this problem. The answer is 1,366. And we solved it in 1 single line of Python, which is pretty cool. Let's check. It worked. This problem, because of the length of it, it was just 1 line. I'm gonna give 1 sound effect. Okay. Great. Now, on to problem 17. Don't forget to like the video. Okay, so let's take a look. What is problem 17? It's called number letter count. And I'm going to go back to the problem. Okay, so if the numbers 1 to 5 are written out in words, so like this, 1, 2, 3, 4, 5. Then there are this many letters used because 1 has 3 letters, 2 has 3 letters, 3 has 5 letters, so on. So if the numbers from 1 to 1,000 were written out in words, how many letters would be used? Okay, well, I don't think I'm gonna do this by hand. It is technically possible, though. I think it would take someone maybe an hour. Okay, an hour is a bit short, but it would take a while. You could stumble. Well, you could get the right answer. Okay, and it says here in the notes, do not count spaces or hyphens. For example, 342, which, and they used a hyphen here, contains 23 letters, and 150 contains 20 characters, 20 letters. Okay, so really, we're just going to count the alphanumeric, well, alpha characters. Alpha characters? The letters. Yeah, the letters. Okay. How are we going to do this? I think we're going to have to use a lot of if statements. Let's find out which language we're using, and then let's start coding, or maybe I'll explain some stuff and then we can start coding. Let's go to the wheel of names, and roll the wheel. I think we're getting Java. No, Python. Again, that's Python again. That was very neatly centered on Python. Okay, that's great. Python is, I think, the easiest language for this. All the languages are very similar, but Python has that nice test syntax. So let's create Python file problem 17. The Python. Oh no, I accidentally made a typo there. Okay. Oopsie. There we go. Okay. So, let's print. Snakes. Yeah. Python. Okay, so run this, see if it works. And we got snakes. It's working. Next. Let's see. Okay, I think we're gonna need 2 arrays. One for little ones, so it's gonna have. And the more I think about it, the more I realize it's probably just gonna be pretty tedious. So, 1. Well, I guess, yeah, 1. We're not going to include 0. 2. Let's just copy this 50 times. 1, 2, 3, 4, 5, 6, 7, 8. 8. Just one misspelling could give us hours of debugging. Okay, hours is an exaggeration. A lot of debugging. And I'm not going to include 10, so we have 9. This is an array of 9. And then we're going to have the 10. This is going to be another array. So we're going to start with 10. And we're going to have a bunch of different. Then we're going to have 20, 30, 30, 40, 50. I don't want to misspell it. Is this the right spelling of 40? How do you spell 40? 40. Oh, it's 40. Okay. 40 it is. 50, 60, 70, 80, 90, and we don't need 100. Oh no, we're gonna need the hundreds as well. Okay. Huh. Yeah, because 1 to 1000. Let's have the hundreds now. Hundreds is gonna be 100. Oh no. Wait, the hundreds are just the 100. They're a combination of ones and tens. So we don't need hundreds. Now, let's loop for 1. So we'll loop end for 1 to 1000. That is inclusive, I believe. So we'll stop at 1. The endpoint of range is going to be 1000 plus 1. Because the endpoint in Python is not inclusive, and we get a colon here. Let's put end using test. It worked. So, whoopsie. Wrong keyboard layout. Go. Back. Okay, so we want to convert n to a string. Let's see. So if n is under 10, we're gonna. If n is under 10, then let's check first if n is 0. That's a special case. If n equals 0, then we'll just. I should probably make a function for this. Yeah, let's make a function. Okay. So define num to words. This converts the number n from the integer form to words, and we can move these variables into the function scope because we don't need them anywhere else. So if n is less than 10, we'll move this logic in here. So if n is 0, we'll return 0. That's 4. I could return 4 for 4 characters, but that's really hard to debug. In fact, I don't even need all of this. I could just say 3, 5, 5, but that's really hard. So instead, I'm going to use these strings. And plus, we'll get a nice formatted output at the end. Okay, if n is less than 10, then let's... Otherwise, so if n is less than 10 and n is not 0, we want to return the ones of n. So let's think about that. For n equals 1, we're going to get ones of 1, which is 2. That's wrong. We want actually ones of n minus 1, and we're never going to get minus 1 because we've already checked if n equals 0. Great. Let's see if that works. Also, if else, let's just have a fall through, we'll return minus 1, which means we don't have an answer. This is just for debugging. Okay, so if oh, sorry, I just want to print to words. Let's see if that works for Python. Problem 17.5. I spelled that. Oh no. I misspelled it again. Okay. So the output was truncated. Let's just loop from 1 to 10. I just realized we're starting at 1, it can't be 0. So let's not even check for that. And it's still telling me snakes. I don't want that anymore. Snakes, 1, 2, 3. Okay. So 1 gives us 1. 2 gives us 2, 3, 4, 5, 6, 7. Great. Now, what if n is greater than 9? Well, let's see. If n is greater than 9, we're going to want tens. So tens, we'll look at the tens. So if n is 10, if n, or rather, if n is divisible by 10, perfectly divisible by 10, we're going to return the tens of n over 10. So if n is, let's say, 10, 10 divided by 10 is 1, so we're going to get the first 10. Well, it's actually the second 10, so we're going to subtract 1 from this. If we were using Lua, we would have to subtract 1. Okay, now let's test this for 100. 1 to 100. Okay, it says list indices must be integers or slices. I think the reason it's complaining is because Python thinks this is going to be a float, although we know it's always going to be an integer. So, because n, oh no, I meant to do this, equals 0. Okay, now it shouldn't complain. Did it still complain? 10, it is 10. If n is perfectly divisible by 10. Not sure why this is complaining. It's not gonna give a float. Let's trick Python. Let's do integer division instead. I think we have a logic error. It says list index out of range for 100. Why is it out of range? Because, oh, we don't have 100, so actually we want to limit to 99. Okay, great. So, what are we doing here? 99, is it working? 90 gives us 90, yes, good. 80 gives us 80, perfect. Next, what if n is not perfectly divisible by 10? So what if it's not 80, 90, or 70 or something like that? Well, then we want to say 80 plus, concatenate it with whatever number of ones we have. So otherwise, we want to say, we'll return the same thing here, plus ones of n minus 1. Let's see if that works, and I have a feeling we're going to get some duplication. It says list index out of range. That's because if n is... Oh no. Why would it be out of range? It got stuck at 11. So what's 11 minus 1? That's 10. Oh, that's wrong. I want to say n 110 to get the remainder of division by 10. It gets the second digit, really. Okay. I do want to append a space, just to be neat. Doesn't really matter for the problem. Okay. 7 results in 67. That works. 60. Okay, we have a bit of duplication though. That I think we could possibly avoid. But we'll see how it goes. I think we could get rid of the duplication later, if we are gonna do that. Okay, let's go. Now we want to get numbers from 100 to 999. And we want, so let's change this to an else if. If n is greater than 10. Sorry, if n is not less than 10, which means n goes from 10 to 99. So if n is less than 100, if n is less than 100, I'm getting an error here. It says I meant to say it's less than 100. Let's see. Is it working? Oh no, we have an error. Look at this. 11 gives 10 1. 12 gives 10 2. 13. Oh, we have an error. Because really we want to be giving 11, 12, and 13. So if n is between 11 and 19 inclusive, then we want to give it the fancy English way of saying those numbers, because we have special names for those numbers. And actually, a lot of, well, I think other languages don't use this. Some other languages don't, and I think it's a lot clearer. All right, let's go. What was I doing here? Okay, what can I call this? Are they tweens? Oh, they're teens, I guess. They're teens and tweens, but I'm just gonna call them teens. So teens is gonna be 11 is the first teen, then 12, not really, but 13. Okay, 14, I can just be 15. I'll remove this. Okay, 15, 16, 17, 18, 19. Is it 19 like that? Yeah. Chat, tell me if I've spelled any of these wrong, because maybe I have. Okay, let's go. I really hope I haven't spelled any of them wrong. Let's see, what was I doing? Yeah. Ah, yes. Okay, so if n is less than 100, okay, so if n is between, I think we can use 11 is less than or equal to n, and which is less than. This is the sort of math notation that I think Python allows. Yeah. Then we're going to return teens of n minus 10, because, well, minus 11 actually. So for 11, that'll give us the 0th teen, which is 11. 19 will give us the 8th teen, which is, oh, was that right? 11, 1, 2, 3, 4, 5, 6, 7, 8, 9. You want to get the 9th? Am I making a mistake here? Am I making a mistake? Oh, yeah. Ha. 0. Oh, 8 is correct. Because the 8th index is really 9. Okay. I just got confused there, but it's clear now. And I realized we don't need these else statements, because if we're returning, it's going to skip the else anyway. So let's get rid of these else statements. I think that's going to help us a bit with the nesting. There we go, like that. Oh, that's much cleaner. And let's see the order. Let's swap over the order. Okay, that should work. let's see. Oh no, I don't have an if statement for this. Okay, if n is less than 100, then we can return that. Right? Now I'm confused. Oh no, this has to be nested. Yeah. Okay, like that. That works. Okay, now I'm gonna go through every single number that we did. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Who would have thought it's so hard to make a computer count? 26, 27, 28. Oh, this is going to be right. And we go until 90. Great. Now let's do the numbers from 100 to 1,000. So 101, 102, 103, 104, so on. 110, 111. Oh, okay. We're going to have to reuse that block of code for the teens. So let's see. We will... What are we doing here? So if n, after all this, it's not less than 100, then it's going to be less than... It's less than 1,000. Well, no, actually, we don't need that if statement, because that's the last check we're doing. So, let's see. What are we going to check for first? Let's check if n is perfectly divisible by 100 with a remainder of 0. If that's true, we'll return 100, 200, 300, sort of stuff like that. Okay, so the way we can do that is just by saying we'll return hundreds. Oh no, we don't have a hundreds array. Okay, so we'll return the ones of n minus 1, then we'll add 100 to it, like that. So let's think about this. What if n is 100? Well, it'll give us ones of 99, which is definitely not what we want. We want to divide n by 100 before we do this, and I'll add brackets for clarity. Division does go before subtraction, but it is good to be clear always. Okay, let's do this example again. So if n is 100, then we'll take ones of 0 and append 100, the word 100 to that. And if n is 2, we'll take, sorry, if n is 200, we'll divide 200 by 100, and that gives us 2 minus 1 is ones of 1, which is great. That's going to give us 2. Let's test this out with 100. So I'm just going to go 100. 100 worked. If we update this to 200, it should work. Yes, it did. Great. Okay, so now we're counting, kind of, but we're still missing some cases. We want to count, let's begin by counting numbers from 100 to 110. Great. Okay, so if n is less than 110, then we can return the 100, 100. Oh wait, but aren't we gonna have to reuse this for numbers like 200? So what if n is 210, let's say, or 205? It's the same logic. So we want to, oh, you know what, I should scroll up here like that. Okay. Righty. So if n divided by, if the hundreds place in n, that's really what I mean. If n divided by 100 gives us a number. Oh wait, if n minus. So we're trying to get the ones place here, the 100. That should give us the ones place. Or we could just... Could we mod by 100? Would that work? Oh man, that's... Yes, that would work. That would get us the last 2 digits, which is what we want. So if n mod 100 is less than 10, this is going to be for numbers such as 101, 102, 103, or 209, but less, not 210. Then let's say we're going to return this, the same thing, and then we'll also add and then we'll add that, we'll add ones of n mod 100, and I have a lot of code duplication here, but really it's just a Project Euler problem. It doesn't have to be that clean and maintainable. Okay, let's see. Why is that work? Is that working? I have to test it. Let's test it for number like 205. Okay, so that gives us 206. Oops, what's that? No. Sorry, my keyboard is acting weird. I need a few seconds to fix it, maybe a minute, I don't know. Okay. It's working. It's working. I have a really expensive mechanical keyboard and sometimes it still glitches. But it's worth it because it sounds great. Listen to this. Okay. Okay, so what we've been doing here, 100 and the zeros. Oh! Look, you know what? We can just call the function again and append 100 to it. Right? That would work, right? I think. And, so 100 and, you'll call the function. What's the function called? Number to words. Called with that. Okay. That should work. And we can also use it perhaps here. No, that's okay. Okay, what about if that works, then I think we can do that for the rest of the cases, except 1000. If it's 1000, so if n is not 1000, then we can do this. I'll indent it. If n is 1000, and we've gone through all the checks, if n is 1000, oh, I meant to say 1000, not 100 here. So if n is 1000, then we're going to return 1000. I'm just hard coding that. And if not, I'm going to throw an error because we made a mistake and we're not supposed to use this function for numbers under 1000. Sorry, numbers over 1000. I'm not sure how to throw an error in Python. Return error, is that a thing? Do we pass errors by just returning them in Python? Make an error. Oh, it doesn't matter. I'm going to return -1. No, I'll return panic. There's no panic in Python. Okay, we're returning unknown. Unknown. Okay, and oh, no, I guess that kind of works. Okay, if it's unknown. And this is sort of an edge case. Let's move it to the top. So it makes it clear that this is not implemented in the core logic. Also, I think that means we can get rid of this. And if... Oh no, and then we'll return unknown. If and this is a bit not unnecessary. Oh, you know what? This is unnecessary for Project Euler. Let's forget that unknown thing. Okay, great. Now let's test it. See if we've actually made a function a way to whoops, to print all the numbers from 1 to 1,000. Let's see. Oh no, it's giving us an error on line 41. Less than is not supported between instances of string and int. Yeah, but shouldn't n be an integer? Why is it a string? Why would it be a string? No, I'm confused. I must have called them towards here. Oh wait, let's look at the traceback. Okay, so in the traceback it says this is where the problem occurred. And okay, that seems odd. Ah, I see now the problem. I should have taken out this one, because we don't want to call it with a string. We just want to call it with this number, which is from 1 to 100. So let's run that again. And we should get all the numbers. I'm going to review a few of these. Just the important ones. Okay. 960. Yeah, that's right. 923, that's right. 799, 800, that seems correct so far. Let's go. Does 1,000 work? Oh no, we didn't check 1,000. We should be checking 1,000 though. Ah, yeah, 1,000 plus 1. Oh no, I lost it. Oh, okay, we're back. Okay, so I checked 1,000. That works. Great. Now we have to sum the amount of characters we get. And we can do that by just making a sum variable. Oh, can you guys see the console? Oh no, you can't. I'm sorry. It's been cut off, isn't it? Yeah, okay, that's better. Decrease. Okay. So, I'm going to return. No, wait, here's my sum. Oh, I can't make a variable called sum in Python. That's a function. Okay, we'll call it total. So total plus is assigned to that, and it's going to be the number of alphanumeric characters in that. So I'm going to call the sum, and we can use that nice list comprehension, or whatever it's called, list comprehension. Yeah, that's the one. Okay, so I'm going to comprehend for. I'm going to take this is going to result in some very unreadable code. So instead of using list comprehension, I'm going to do it the normal way. For each character, we'll make a variable called words, and we'll set it to num to 1 to n. For each character in words, will increase the total by 1 if C is equal to is alpha in Python returns true if the character is a letter, and false otherwise. Else 0. Great. Okay, so now I am going to get rid of that. Python does not have an increment operator. Anyway, let's test this for numbers from 1 to 10. Let's see if it actually works. Now let's print the total. So print total. Run it again. We got 39 characters. Oh wait, they already did 1 to 5, so that's a good test. I don't have to check it myself. And it says 19. It gave us an answer of 19. Well, that's correct. Let's test it from 1 to 1,000. It gave us 211, 21,134. And we should be done with this question. Let's have a drum roll. Drum roll time. Uh-oh, it's wrong. That's not good. Okay, let's go back to problem 17. I may have made a spelling error. Could I have made a spelling error? Let's see. 11, 12, 13, 14, 15, 16, 17, 18, 19. It seems right so far. 70, 80, 90, 10, 20, 30, 40, 50, 60, 70, 80, 90. 1, 2, 3, 4, 5, 6, 7, 8, 9. It seems right. 11, 12. Oh. 12 is not. 12 is not how you spell 12. 12. So without this extra E. Okay, so our initial answer was an overestimate. So I'm running this again. I believe we got a different answer, did we? Yeah, we got a different answer. 12. Run it again. Okay, here we go. Okay, this should be... Is it right? The past half an hour or something has accumulated to this moment. Drum roll. It is correct. We need 1,000 success sound effects for this problem. Okay, I'm not actually gonna have 1,000 sound effects. I was kidding about that. Alright, let's move on. It's problem 18. Maximum path sum 1. Oh, that has a scary name. That has a very scary name. Okay, here we go. Let's get to the problem. Let's read this. By starting at the top of the triangle below, moving to adjacent numbers on the row below, the maximum total from top to bottom is 23. Okay. Let's look at this. So this looks a bit like Pascal's triangle, but it's different because we're not actually summing numbers. So if we look at it, 3 plus 7 plus 4 plus 9 is 23. And that is the best possible sum you could get. Okay, fair enough. Find the maximum total from top to bottom of the triangle below. Which triangle is it? Let's see. This triangle is pretty big. Oh, it's bigger than that. Oh, it's really big. Okay, fine. As there are only this number of roots, it's possible to solve this problem using root hooks. However, in problem 6-7 is the same challenge. Okay, well, this is not problem 6-7. We're not going to respect that number because of all the brain rot it has inflicted upon many people, including myself. Okay, it's actually not that bad, but we'll solve this problem, not that problem. Okay, so I think we can brute force this. Let's paste this into. Oh, I found an interesting pattern where we only have two choices, right? And if we align these numbers horizontally, really you can only stick in the same. Sorry, not horizontally. But yeah, you can either stick in the same column or move to the column to the right. Those are your two options for each row. Okay, let me illustrate that after we choose the programming language for this problem. Let's go to the wheel. Time to spin the wheel. What language are we gonna get? We got C again. Alright, C is great. So I'll make a new C file. It's problem 18, right? Oh, I forgot to update that. Problem 18. Right? Yeah, okay. So I'll go make file problem 18.c sharp. Sorry, .c sharp. And what was it? What do I take here? 1 second. Gonna drink some water. Okay. So make the windows look good. And we'll go back to the code. So we'll have we'll make this into an array. You know what, I'll paste it in here. And as you can see, if I paste it like this and all the numbers are aligned, the only options you have are to go straight down or to go one step to the right. So if I turn this into an array, then I go to index I or index I plus 1. Anyway, let's make an array after I write the boilerplate. So include some stuff, standard input and output, like int main, void. All right. Okay. So in order to make, let's test if this is actually working. So we're using the C language. C. And we need semicolons. Oh wait, yeah. So it's gonna be GCC problem 18.c, and then you want to run that exe that it produces, and we got it. C, there it is. C, it's there. That's a pun. Pun intended. Okay, now let's make an array. We'll call it, I'm going to call it triangle. So it's going to be a 2D array of integers called triangle. So triangle, assigns that Why isn't that working? How do you make raisins? Let's see if this works. We have 3, 7, and 4. 2, 4, 6. I really shouldn't be copying this by hand. And yet I am doing it. 9. 3. Okay, I'll check it to make sure it's right. Okay, it is right. Okay, it says an array may not have elements of this type. Too many initialized values. Is it an int array like that? No, I don't think so. Let me just quickly check. Oh no. This is going to be hard to see. We're going to have to... Okay, I think I know what to do. Oh no, I didn't do that. Okay, so this works, but we can't actually have a 2D arrays with dynamic sizes in C. I mean, we could, but it would be impractical. So instead, I'm going to make it 4 by 4. And that's going to have some extra space, but it's okay. Now let's loop over the array and see if it works out. For this is going to be row. First we'll loop of rows. Oh, we'll set the row to 0 to start, while the row is less than 4. We'll keep incrementing the row. And really I should call it R instead of row, because that's easier to type and it flatters the code less. Also, I'm going to zoom out a bit here so you can see the question. Okay, there we go. So, what was it? Return. Ah, yes. Now we're going to loop over the columns. That. Indentation. I'm just going to change this R to C for the inner folder. And then, oh, you know what, actually? I need the column number should be less than the row number. So, for example, for row 1, the column number is going to go from 0 to 0. For row 2, it's going to go from 0 to 1. Also, I'm going to make the code a bit bigger. There we go. Okay, let's see if this works. I'm going to print the number at the position in the triangle. So triangle of row of column. And then after every new row, make a new line. So this should give us a nicely formatted triangle. New line. No, stop there. There we go. Okay, so we got 7, 24. Oh. Column should be less than or equal to the row number. Yeah. Okay, there we go, that's better. So 3, 7, 4, 2, 4, 6, 8, 5, 9. Great. Now, we want to look through each path. Let's think about this. Each path, how are we going to express the paths? Each path is going to be, oh no, okay. Each path is going to be either left, which is going down in our case. Let's call it down. And D for down, and R for right. So each path can be expressed as a string like this. Down, like that, for example. The winning path for this small triangle would be expressed as down, 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 right, right, right. Make sense? Yeah, it does make sense. Okay. So we could also, instead of using letters, we could use binary numbers. Let's say 0 represents down and right 1 represents right. And so if we counted in binary, which is quite it's the same as counting in decimal really, but if we counted and thought of a binary number, then we would get all the different paths. So we would have to count from 0, 0, 0, 0 to 1, 1, 1, 1. And that's the same as counting from 0 to this number is 15, I believe. Yeah, it's 15. Okay. So let's do that. Let's count and we'll see the binary value of the number. How are we going to count? Well, let's use a folder to count. So I'm going to make an integer called path. Starts at 0, binary. And I know this is the same as decimal 0, but it's nicer to think about it if we do it like this. So while path is less than 2 to the power of, and in order for us to have the power function, we're going to need to import the math library. Patrick says, in the end, everything is just ones and zeros, and he is correct. Okay, so how double x? Okay, so we're going to multiply 2 to the power of the length of the path, which in this case is 4. And while the path, and then we'll increment the path every time. Great. Now let's print the binary formatted path. See if that works out. I don't think we need this loop anymore. Oh, okay, we got a bunch of errors. Printf is what I meant. I also need a semicolon. I could have just read the stuff in VS Code. And it ran. It printed BBBB. Well, that's not what I meant to print. Is this the wrong format? Let me Google the binary formatting. The binary format specifier. Oh wait, am I right? Am I actually right? As of C23. Okay, the new format specifiers are B and B. Yes, but that's what I used. That's exactly what I used. Am I not? C23. Oh, I'm not using C23. I'm probably using something like C20. Oh no, less than that. Former. Okay, what's the original answer? That's annoying. Can I update my C version? Oh, you know what? We don't really need to print it as a binary number. It's okay. Let's forget that and go back to the normal way we were compiling it. So does it work? No, but we don't need to know. We'll just print it as a decimal for now. And that works. We can add a new line. And we're counting. Yay! But we think about this. What digit do we want to find? Well, we want to loop through the rows, and we want to once we're looping through the rows, we want to think about which binary digit corresponds to down, what right. So I'm gonna start looping the row while the row is less than, say, 4. We'll increment the row. And that's great. So now I want to map the binary digit to the row. Does that make sense? I hope so. Let's see how can I map a binary digit? How can I get the nth binary digit in a number in C? Well, I can use bitwise operations. I think if I did something like, let's see, path shifted to the left. Do I want to shift to the left? Or do I want to shift to the right? Well, let's think about this. It doesn't really matter, actually. But let's say that the leftmost binary digit represents the first path movement. Okay? So, I'm going to... That means that I have to shift to actually the left. So I'm going to shift to the left by row, and then I'm going to say... Oh no, it's easier if I shift to the right. Okay, let's say the rightmost is the first. And then once I've shifted to the right, I'm going to take the leftmost digit, and I can do that by doing a binary AND with 1. So that's going to give me the last digit, so 0B1. Great, and I don't know why that's wrapped in an if statement, but it is. Actually, I didn't mean to wrap that in an if statement, did I? Oh, I did. Okay, well, I did then. And I'm going to, if this is true, then I'm going to look at the number which is down. So this is going to represent a down. 1 is representing down, right? No, 1 represents right in my previous example. Okay, great. So if I'm going right, that means I need to print. I'm gonna have a print. Yeah, I'm just gonna print it for now. Later we'll add it to the sum. But I'm gonna print it, and I'm gonna print the... Oh, you know what? I should have a variable here called column. I'm gonna set column to 0 to start. And then I'm gonna increase column if we're going right. So column plus plus if we're going right. And if we're going left, then I want to increase the row. Only the row. And I think we always increase the row? Yeah, we do. So we can get rid of this else statement. And now let's print this. This should go through all the paths. So let's print f. We'll print whatever number is at the grid. What did I call it? Cells or grid? Triangle. I called it triangle. At the triangle of the row and that column. I said cow, not column. I meant to say column. Okay. Row and cow. And I forgot to add a new line specifier here. So let's add one. Okay. So for the first path, we go 3. This is 0, 0, 0, and it's just a bunch of downs. 3, 7, 2, 8. Okay, then we try. It says 3, 7, 2, 8, 0. Well, that's wrong. Right? Isn't that wrong? Why are we getting a 0? We shouldn't be getting a 0. Did I make a mistake? Possibly. Why would we be getting a 0? Okay, let's add an extra new line so we can know when when we reach a new path. Okay, that's much neater. So 378. Okay, the second part starts with a 0. How could that be? Would be 0. What's the first thing that we're indexing here? It's gonna be the rightmost cell is going to be 1. Wait, let's actually print. Yeah, that's gonna be 1. So our path is going to be 1 right turn, and the rest is going to be left. I mean downs, because we're thinking of a left turn is down here. So we're gonna start by going right, and that puts us here in the nothing. So we can't actually go right without first increasing the column. So we should start at column number 1. Oh, but we also need some. Okay. How are we going to do this? How are we going to do this? Let's see. Let's see. Is row getting bigger? Now I'm confused. Okay. Let's try and I think row increases at the start, which is not what we wanted. So we can only increase row once. I mean, sorry, we can only increase the column once row is already at 1. Am I right? Ah, do we want to print triangle of row plus 1 and column? That can work. Actually, that could work. And then we go from 0 to 3. I'm not sure. So 7 to 8. Yeah. Kind of. 4, 4, 5. 7, 4, 5. That's going through a bunch of different things. So then we could just add the 3, the top. Maybe. Oh wait, could I? I guess I could print a decimal. If only I was using C23, I could use the binary formatting. Okay, let's print the path. 7. The path is 0. The path is 1. Oh. Okay, well, you know what? You know what? I think this works if we also include the row 1, the row 0, and column 0. Let's try that. Three, 7, 2, 8, 3, 4. Oh, that's good. 4, 5. 3, 7, 4, 5. let's see if it works. I'm gonna make a sum variable. So int sum, that's gonna start at triangle 0, 0. And we're going to increase sum by the value of this, like that. So let's see how that works. And then in the end we can print the sum. So print that mod d decimal specifier printing sum. Oh no, sum here. And I guess we'll see if we get the best sum of 23. Where's it printing the sums? Shouldn't it be printing a lot of sums? Oh, it is. There we are. Okay, but the sum is way too big. Okay. Oh, I know what's happening. I just didn't format this correctly. Let's try again. 3, 7, 2, 8. That gives us a sum of 20. 3 plus 7 plus 2 the same. Yeah, that gives us a sum of 20. Okay, that's good. 3, 4, 4, 5. Sum of 16. Alright, so the best sum here that we get should be 23, and it is. So that's good. I think the algorithm is working. Let's just now make it find the best sum, and then we'll be done with this problem. So int best sum starts at 0, and if we find the better sum than what we already have, we'll update the best sum accordingly. So if this sum is greater than the best sum, we'll set the sum. Sorry, we'll set the best sum to the sum, and yeah, it wants us to find the maximum total. So in the end, we'll print what our best sum was, and it should be 23. It is 23, good. Now the hard part is going to be updating this code to work with the big triangle, which has many, many columns. The big triangle has lots and lots of columns. How many? I think we're gonna have to count. Let's count. How many columns does this have? So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 columns. Let's count that again backwards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So 15 appears to be correct. Good. Now, let's make a new array. Well, we'll just update the size of this array to be 15, and then I'll also update this power for 15, and the row should stop 14. And now, time to paste this monstrosity in. There we go. Don't think C. Okay, so we'll just fix the indentation. There's the indentation fixed. Now we can go down a bit. Add the square brackets. I mean the squirrely brackets. That's what you call them. I should have also had a comma while I was doing that. There's the comma. And now I need to add commas here too. There's going to be a lot of commas. Okay, let's. Oh no, I'm sorry. I forgot to show the code. I was just adding commas in here. Okay, we're back. And I accidentally have the caps lock on. It's not good. Can't turn the caps lock off. Caps lock is broken. This is not. Oh, I think. Oh, there we go. It's fixed now. I just need to restart my keyboard manager thing. Which hopefully it's done. Great. Okay. So, let's add a bunch of commas. How are we gonna add a lot of commas? I don't know. I can think of one way to do this. But the rest of the ways don't really make sense. This is gonna be annoying. It's okay. Okay, so we'll add a comma here. I want a comma there too. Is the word wrap messing up? Why can't I go down? Is that oh, that's on the same line. It shouldn't be on the same line. There we go. Now it's on a different line. I'll insert a comma there. There. What if I inserted one here? Okay. It's not perfect. It's not perfect, but I'll correct the mistakes later. Oh no, I meant to insert comma. Let's comma. Yeah, my keyboard has blank keycaps, so it's hard to find stuff sometimes. Okay, now I've got all of the commas that I need. Right? I hope. I mean, I've got a lot of commas. So let's try and remove these commas, the stuff that we don't need. And I'm also going to remove the trailing commas. We definitely don't want, I mean, not definitely, but I prefer not to have trailing commas. Maybe there's an easier way to do this, and I'm just missing it completely. Maybe not. Maybe this is the best way. Maybe, no, you know what, I'm sure someone more experienced in them could find that. Oh my god, I didn't do all of it. Ah! Yeah, that was the worst scream I've ever heard. Okay, let's decrease the font size a bit and turn off line wrapping. Word wrap. Decrease editor font size. Okay, we can afford to have a bit bigger than that. Anyway, so it's not that many I missed actually. Not so bad. Not so bad. I just hope I didn't mess up any of the numbers. Invalid octal digit. So, I'm pretty sure C considers numbers that start with a 0 to be octal, which is base 8. So it's not actually possible to have a base 8 number that is 9. So all the digits less than 8 would work if you start with a 0. Anyway, I'll just replace that with a space. It is nice to have these zeros here, leading zeros. And octal 4 is the same as decimal 4, so it doesn't matter. Anyway, let's run this. See, it shouldn't take that long. And it gives us this number here, which is the sum of the best sum we've found for any root. Let's see if it's the correct answer. Drum roll time. Drum roll, drum roll, drum roll. Uh-oh, that was bad. It's wrong. Now, I hope I made a logic error in the code and not an error when I was messing with these array things. Because a logic error would be much easier to debug. Okay. So okay. So let's take a look at this code. What's wrong with it? What could possibly be wrong with such good code? Yeah, that's how I sounded. best sum. So I'm updating the best sum accordingly. And it starts at 0 and gets updated many times. The binary shifting seems to be correct. What's my mistake here? Well, I'm using 14 here because I'm including the first thing in the sum. Oh, but do I have to start row at 1 and end at 15? I'm pretty sure I do, actually. Yeah. Oh no, but I'm already adding 1 onto row. So, what about when I'm shifting? When I'm shifting, am I shifting by the correct value? Shift by 1 to start? No. I was shifting correctly before. Okay. Maybe I could simplify this code and then it would be easier to debug. Let's see, how can I simplify this? Can it get any simpler, actually? I'm not sure. If only I could binary format the string. How can I update my C? Maybe if I have Clang, maybe Clang uses the right version of C, or C-line, whatever you call it. I don't have Clang. What's the tiny C? C? No. What are the others? What if I debug this? Is it going to use GCC? You know what? Let's put a breakpoint in here. Gdebugger. No. Gdebugger, that could work. Project A does not exist. Oh no, the debug is not working. It's okay, I'll just use print statements. Is it even a sum? Let's do this. Have some water. Is it correct to right shift? Okay, I'm gonna take a break and think about this. I'll be back in a few minutes. Can I put the... Be right back. Be right back. Yes. Okay, bye guys. Hello? Hello, I'm back. And I debugged the code a bit. And I realized I have two major mistakes. Well, one of them is more severe than the other mistake. And that is, if you take a look at the triangle array here, it is this length 1, length 2, length 4. As you can see, I've skipped completely row 3 of the triangle. Row 3 is very important. It's gonna give us the wrong answer if we skip it. So I'm gonna add it back now. 4782. And there is one more error. It's too many initializers. Now why is it too many? Oh no, and this is duplicated. Okay, so we remove that. So now it's perfect. And also this should be 2 to the 14 because we only really ever make 14 direction changes, so down or right. Let's test that out, and it should give us a different answer. It does. It gives us the answer 1074, which works. I hope. I haven't actually checked it. If it works, I'll play the sound effect. Come on, come on, come on. Yes, it worked. Yes, very cool. All right, great. I think that was the hardest problem to solve so far. So let's go back to the problems page. And I was talking about how I really didn't want to make a mistake when I was inputting the numbers, and I did, and it cost me a lot. Okay, the next problem is called counting Sundays, and let's read it. Okay, problem 19, you're given the following information. I'm not going to read all of this, but it seems to be a bunch of information about the months, how many days the months have, and when the leap years occur. Question is, how many Sundays fell on the first of the month during the 20th century? Wow, okay, well, I think the most obvious way to solve this is by just looking through every single day. And I guess I could use some sort of library for that. Look at all the dates. But since the problem has given us this text, all of this stuff, I think it expects us to write that stuff from scratch, which could be fun and educational. So I'm going to do that. Let's spin the wheel and see what language I get. Okay, I'm hoping for, I'd like maybe JavaScript. We haven't done any JavaScript problems today. And, oh, yes! We got it! Thank you, Wheel. You deserve a round of applause for that. Okay. We got JavaScript. Let's make a new JavaScript file. It's problem 19. We're getting close to 20. I think 20 is a good place to stop. We'll see. Okay, so I'll move back to the code. Hopefully you can see that. I'm going to test this by printing something to the console. Yada. Double with a double Y. I don't know why I spelled that. Double Y. Okay, let's go. Problem 19.javascript. And it worked. So let's make an array to... First of all, what day was the 1st of January? Because if we're going to loop and find out the days for every single day and see which of those days is a Sunday, we're going to have to know what the 1st of January was. And there's a neat trick. So there's 365 days in a year. And that means that is divisible. That is actually divisible perfectly by 7. So if you just add 1 onto the day, for example, if the 1st of January 1900 was a Monday, then because 365 days passed, and on the day 1 of 1901, which is the 1st of January 1901, we're going to get a Tuesday. Was it a leap year? Because a leap year actually includes 356, because 29 instead of 28 in February. But oh, what is 1900 divisible by 4? Let's go. 1900 divided by 4. It is divisible by 4. So, but not on a but not on a century, unless the century is divisible by 400. Okay, that's pretty interesting. It's pretty hard rules. I guess they really want to keep their daytime cycle in sync with the sun. I mean, yeah, it's pretty important. Anyway, so let's begin by making an array. I'm gonna make an array. So const, let's say, I don't know, month lengths. Let's call it that, month lengths. We'll initialize it with the length of each month, and I'm not going to use semicolons in JavaScript. Don't take me for it. Okay, so what are we doing? January has how many months? I mean, how many days? How many days does January have? January has it's somewhere here. 30 days is September, April, June, and November. I should have memorized this. I'm not very good with the months, actually. The months of the year. All the rest have 31. Okay, well then, 31. So January has 31. I'll add a comment there. February has 28. That's February. Or 29. February. We're going to have to be careful with February. I don't know why I added a exclamation mark. That's stupid. And I'll just put this 28 in brackets. Next, January, February, March. I don't want to make a mistake here. I made a mistake with the last data inputting, and that was terrible. I spent so long debugging that. Okay, so January, February, March. When is March? March has 28 days. April has 30 days. Why would I say March is 28 days? March doesn't have 28 days. March is 30 days. No, March has 31 days. Okay. January, February, March. April. May. Whoopsie. May. Oh no, that's not what I'm supposed to type. I'm supposed to type, yeah. Okay. May is going to have how many days? 31. June is going to have 30 days. Oh man, if only I had memorized the months of the year, this would be much faster. Okay, July has how many? It's normal, 31, right? So all the rest have 31. I've got to update that comment. Okay, what else? June, July, August. August is the next month. August has 31. September has 30, as it says here. Wow, this is really tedious. September, okay, then we have October, has 31. I remember that because Halloween is on the 31st of October. Right? Yeah. Then November, Jesus. November has 31. December. We're in December now. Christmas time. December has 31. Yes, good. We're done. We're done with listing all of the months of the year. That was very tedious. Now it's time to check, which is going to be even more boring. Okay, let's go. Hopefully at some point we can jump into the code. So January has 31, right? Yes. February has 28. March 31. April. Good, 30. May. June has 30. July 31. Oh my, August has 31. September 30. October 31. November has... Oh, November has 30. Good spot. There we go. December has 31. Good. Alright, let's start the looping process now. I don't know why I said it like that. I just thought it would be good to say looping process. Looping. Okay, whatever. So let's make an integer. This variable is going to keep track. It's going to be sort of an enum. Can I make enums in JavaScript? Ooh, enumerate. No, we can make enums in TypeScript. Unfortunately, I'm not using TypeScript, so I'm just gonna say const day, and the day we're gonna start on Tuesday. Because remember, I said the 1st of January of 1901 is a Tuesday because the last one was Monday. That's how the years work. So Tuesday is gonna be. Let's start on Saturday. What should day 0 be? See, Saturday, Sunday. I'm gonna make day 0 Sunday. Okay. So Sunday, Monday, Tuesday. So Tuesday is gonna be 2. And let's see, what else do we need to do? Now we want to start increasing the day, depending on the month. We start in January. So 4. Well, we want to loop through the years. Okay, I'm going to make a for loop. Let the year start at 0. No, let the year start at 9. That's when time started, guys. 1901. Okay, no, that's not when time started. Year starts 1901. Yeah, it's less than. And what? When are we going to stop? We're going to stop at 200. 2000. We'll just increment year, every iteration. Okay, then we want to look through the month. For that month, which is going to start at 0. It's going to stop at 11. Just realized something. This should be less than or equal to. And I'm going to increase month every time. Okay. Great. So, looping through the months and the years. Now, I think I could add on today. I could just add months of month lengths. That's what I call the array. So month lengths. That's a hard word to say. Okay. And then if I mod by 7, I'm gonna get the day. But we want to get every day, right? So I don't think that's gonna work. Let me make the code a bit bigger. Okay, I can afford to make it bigger for this problem. What was I saying? Oh yeah, this approach probably doesn't work, does it? What if I divide it by 7? Would that work? I think that could work. I divide by 7 and take the floor. That could figure out the number of weeks that passed, but I want to... You know what? Instead, I am going to do this. I'm just going to loop through each day, and there may be a better way to do this. I cannot think of it at the moment. Maybe it'll come to me later. So, well, days less than... How many months? Month lengths of month. And then month plus plus. So we'll... No. I meant to say day plus plus. I meant to increase the day instead. Okay. Great. And for each new day... Oh, no, I didn't mean to do that. I can't call this day. I need to call this... let's call it M month day. M for month day. So M day. Get that, paste. Update it over there. Oh, and day, good. Because I don't want to clash the name with this other variable. That would be bad, because then day would get reset. Anyway, I want to... what am I doing with this loop? Why am I even using this loop? Oh, stupid. Instead, I'm going to while day... Oh, now I'm confused again. Let's see, let's look through this code. Oh, also the year started. Yeah, 1991. In this loop, actually, I'm going to use this loop again. I'm going to increase the day by 1. So day is assigned to day plus 1. And I do it this way because I also want to wrap it around every 7 days. So we'll get the remainder of division by 7. And I can get rid of this statement here. Now, this is a very crude way to do stuff. But I can't think of a better way. Okay. So. Now we want to implement leap years. So how are we going to do that? Leap year occurs on any year evenly divisible by 4, but not on a century unless it is divisible by 400. Okay, so the way I can figure out it's a leap year is just by implementing this logic. Although I think it means the only leap year that actually doesn't end up being a leap year because it's divisible by 400 is 2000. And yeah, that makes sense, right? Okay. Instead, I'm gonna make a function which gets the length of the month for a particular month and year. So I'll declare a new function called, let's call it function get month length. It's going to take in, as an argument, the month index and also the year. It's going to check if it's a leap year. So if the index of the month is equal to what? Equal to what? February, which is index 1, then that's where all the tricky stuff is. Otherwise, we're going to return just the month of the index, right? Yeah. Okay. Month length, I meant. Month lengths of index. Okay, so we're returning year, return year. Oh yeah, okay. If index is 1 and year is divisible by 4, so the remainder of division by 4 is 0, and the year is not divisible by 400. Yeah, so the remainder of division by 400 is not 0. It's not perfectly divisible by 0, like this. Then it is a leap year. And I'm going to return 29, because this is February. February on a leap year. I don't know if I spelled February right. No, I didn't. February. Yeah, that's right. Okay. Now, instead of just indexing the array in this for loop, I'm going to use this new function we made. And it's going to be get the month length of month. That's month is going to be the index. And the year is going to be year from the for loop. So yeah, there and there. Now, this should work. And I'm going to check if the day is a Sunday, which is day index 0 in my world, then we're going to increase the number of Sundays. So that's the Sundays count. Also, day shouldn't be a constant. Okay, we're going to increase the Sundays count, which is a new variable I'm making, by 1. So we can increment it. Sundays count plus plus. I may have made, I've probably made a 1 by off error here somewhere, or maybe some other small logic mistake, but I think that we've gotten the general structure, so I'm just going to print the result of Sunday's count and see if it's correct. We got that many Sundays. That is a lot of Sundays. If someone lived 100 years from the 1st of January 1901 to 31 December 2000, which is a long life, by the way, they should be happy if they lived that long. Then they will have, I hope, experienced 5,217 Sundays. Is it right? Have we made a mistake? Let's see. I'm just going to revise this function here. Leap year occurs on any year evenly divisible by 4. So that's right. What about this part? But not on a century unless the century is divisible by 400. Okay, well, this is a mistake, because actually I want this. If the century is divisible by 400, then yes, it is a leap year. But if the century is divisible, well, we're never actually gonna get a century that's divisible by 100, so we can ignore that part. Let's run it. We got a slightly different answer, which should be correct. Let's see if it is. Time for the drum roll. Uh-oh, that was bad. That was wrong. I may have made a mistake. Does... Okay, let's take a look at this. Is 29 correct for February? 28, rain or shine, and on leap years, 29. Well, we don't need the century logic. You know what? I think it's probably in this get month length function that we have an error. But I'm not sure. Let's see. A leap year occurs on any year evenly divisible by 4. So that's this part. But not in a century. Unless it is divisible by 400. Oh, should be an or, not an and. Oh no. I don't actually need any of this code, given our range of dates, because we're not getting any centuries. So. Yeah. Okay, third time's the charm. Come on. Oh man. Okay, let's think about this carefully, but not in a century. Unless... Is the century gonna be 2000 or 901? Is 901 a century? It says here you may do some research for yourself, so I'm going to do some research. Oh, well, it says it's the... What about is 9,000 a century? 900 a century? Does century mean every 100 years, or does it mean... Well, let's see. Is maybe 1900 was a Monday, so actually it wasn't a leap year because 1900 is a century. So that means unless it's divisible by 400, and 1900 is not divisible by 400, which means the 1st of January 1901 is a Tuesday. Sunday is day 0, Monday is day 1, Tuesday is day 2. Am I starting at the right year? Yes, I am. Am I starting at the right month? Month 0. Yes, I am. Am I starting on the right day? Day 0. Am I stopping on the right day? Yeah, it seems so. If the day is 0, we increase the Sundays. And we also increment the day and wrap it around by 7. Okay. Okay. I must be making a mistake here. Is 2000... 2000 is divisible by 400, so it is a leap year. It's also divisible by 4. So in my code, I am including it as a leap year. Now I'm stuck. I am stuck. I'm gonna take a look at my months of the year to see if they're correct. 30 days are September, April, June, and November. All the rest have 31. Except February alone, which has 28 and 29 on a leap year. You know what? I realized I just reread the question. It says, how many Sundays fell on the first of the month during the 20th century? Well, first of the month, that's the part I missed. So, I want to check if M day is 0. That's the only day I care about. So if M day, the day of the month, is the first day of the month, then I am going to... Oh, sorry. That is automatically the first day of the month. Okay. Yeah, here I can add onto the day. I can add the length of the month, get month length. And also, what did I want to do? Oh, yeah. So if the day is a Sunday, then we increase Sunday's count. So Sunday's count plus plus. Alright, I hope this works now. And we got 0, that's wrong. Yes, JavaScript will not give you a warning if you don't pass parameters into functions, unfortunately. So I'm just gonna say year and a month. Oh, it's month first. It's month and year. Okay, and the answer is 171. Is that correct? Well, it seems like it could be correct. Are these lines in the right order? If there's zeros and days count. I wanna... Should I do the calculation first? Like that. 1 Well, that's not. Is that going to include the 1st of January? That's not a Sunday. Oh, that's a Tuesday. Is it going to include the 1st of January 2001? Well, it is. Okay, let's run this. No, okay, that seems right. So, I'm gonna refresh this. Press check. We did it after all. It only took half an hour, which is way too long. Okay. Time to solve problem 19. Oh no, we already solved problem 19. We want to solve problem 20 now, which I think is going to be the last question for me today. It's been a while. So it's the factorial digit sum. It's big. N factorial means n times n minus 1 times n minus 2 times n minus 3, so on. For example, this is 10 factorial. It's basically the product of the numbers from 1 to n, all the natural numbers from 1 to n. Well, not basically, that is exactly what it is. And the sum of the digits of the number 10 factorial, which is this is the 10 factorial, by the way, it's 27. So, yeah, because 3 plus 6 plus 2 plus 8, so on. What's the sum of the digits in the number 100 factorial? Well, 100 factorial is going to be an absolutely huge number. It's going to be 100 times 99 times 98 times 97, blah, 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 blah. It's big. So we're going to have to use big ends. And if we use C, well, if we have to use C for this problem, it's going to be very, very difficult. Because C has no big ends, as I have said many times for these problems. It hurts to remind myself of it, because it is going to be quite a bit more difficult to solve this problem in C. Well, let's spin the wheel and see what language I get. Okay. Let's go. Spinning time. Okay, it looks like we're not getting C. We're getting Python. This problem is going to be incredibly easy in Python. It could be one line. It's going to be like that other Python question we did. Because, yeah, Python integers are resizable. I mean, yeah, they resize themselves automatically. So every Python integer is a big integer, so to speak. Okay, now let's begin coding. So we'll go back to the code window. Bit of a mistake there. Okay, great. So, make a new Python file. This is the last question for today. Problem 20.python. And we'll print. Okay, I like printing snake. Python. No, well, it's print cobra. So ironic to print cobra. Is cobra a type of Python? Actually, now I'm not sure. It doesn't matter. It works anyway, you see? I have cobra here. Patrick says I got lucky with Python. I deserve it. Thank you. I did get very lucky with Python. Yeah. Okay, so next is yeah, we're gonna calculate 100 factorial. Now, you know, Python probably has some built-in math.factorial. So if I import math, I can do math.factorial 100. But that's boring. I suppose maybe I should do it myself. No, let me make the code bigger. Okay, look, this is how easy it is. And I'm going to use a semicolon here. Just to make it one line. This is how easy it is to solve this problem in Python. Oh wait, no, it's not that easy actually. Because I need to find the sum of the digits. So if I want to find the sum of the digits, I want to... Well, first I'm going to convert this into a string. Let's print that. Okay, that's the number. It has a lot of zeros at the end. Okay, so first... You know what, I'm going to use my list comprehension, which is like an inline for loop. I'm going to loop through each character in the string. And for each character in the string, I am going to convert it to an integer. Int c. And I'm going to take the sum of all these characters. It says I didn't close something. I didn't close this bracket. This bracket here, this square bracket. Why wouldn't I have closed this square bracket? I'm confused now. Must have made a mistake. Let me make this code a bit smaller. I have bracket pair colorizer, and yet I still can't find the error. Bracket pair colorizer is not helping me. Oh! I made this error before. I've got to have that close bracket. Okay. There we go. Great. And it's pretty cool. We're finishing the final, well, the 20th Project Euler problem in one single line of Python. Some of the problems were much harder. Well, this would be hard too if it was written, if I were doing it in C or something like that. All right, let's enter 648. Drum roll, please. Correct. Thank you. Thank you everybody for watching. If you got this far, please like, subscribe, it means a lot. And yeah, I think this is it for my for today. I've solved 20 Project Euler problems so far, and still it's a difficulty rating of 5%. But some of these problems were quite interesting. Well, yeah, alright, thanks for watching. See you. Goodbye.